Welcome, ladies and gentlemen, to Pre-Calculus Foundational Skills, week number 2. My name is Brian McLogan, and I created this training to help those of you get prepared for pre-calculus. But I did want to let you guys know what we're going to be covering in this training is specifically looking at fraction operations. We're definitely going to talk more about factoring, rational expressions, trig, and then obviously get into some radicals. So this is all going to be just some foundational skills, again, to help prepare you for pre-calculus. It is not an exclusive of everything you need to know, but just a little taste of some reminders, because obviously we know how last year ended, as well as through the summer, we forgot some things, and we want to make sure we're on the right footing as we get prepared into pre-calculus. One little quick tip as far as you are entering in pre-calculus, I wanted to remind you that students struggle with pre-calculus mostly because of the algebra. Now, that's not every student that struggles with pre-calculus is algebra, but most of the students that do struggle, it's the algebra of pre-calculus. It's actually not a lot of the stuff that we are teaching from a new perspective. Typically, students actually do very well on the new material that I teach in pre-calculus. The reason why most students struggle in pre-calculus, and this was also my experience and when teaching calculus, is the algebra, because they have to apply a lot of the content and the processes that they've learned up to this point in pre-calculus, and either they forgot it or even maybe never learned it or it was never taught to them. So pre-calculus really just exposes a lot of the material that you need to know and remember, and that's obviously the purpose of what we're doing these trainings for, is to build up that foundation. So the goal in this Goal number 2 in this training is to really kind of not only just improve the understanding of those foundational skills, but really the speed. Because, as we're getting into pre-calculus, you start to notice that we start doing, more problems, and you might have some more time tests. So it's not just do you conceptually understand what we're doing, but can you apply them in a time requirement that is going to, satisfy a given test or whatever may be the case. Because some of these problems are going to be multi-stepped, right? And you're not going to want to spend so much time doing something that that you could do a little bit quicker if you have those practice ahead of time. So let's go ahead and get started with fractions, because a lot of students will look at 1/5 minus 2/3 and they say, oh, I'm just going to plug it into my calculator, right? Or convert them to decimals, or whatever may be the case. But it's really important to have a foundation of fractions, because when we get into more advanced problems with rational expressions, we need to have that understanding of how to apply fraction operations so that we can quickly apply that to more complex problems. So case in point, in this first problem, I have 1/5 minus 2/3. Hopefully, if you remember that whenever adding and subtracting fractions, we need to apply a common denominator. So the first thing I'm going to do is identify my least common denominator of 5 and 3, which is going to be 15. Because 15 is the smallest number that 5 divides into evenly, as well as 3 divides into evenly. So therefore, to obtain my common denominator, I'm going to multiply by 3/3 on the left-hand side and a 5/5 on the right-hand side. Now again, remember, this isn't always the case, right? Again, just remember, if this was 1/6 minus 2/3, well, then my LCD would not be 18, but my LCD would be 6, right? So just make sure you understand that you're trying to find the LCD is the common denominator that both denominators evenly divide into. A trick is just to multiply the denominators, but that's not always the case. And up here, case in point, here the LCD would be 6. All right, so now when I go ahead and do that, I get 3/15 minus 10/15. All right, and now that I've obtained a common denominator, I can just apply the operation. In my numerators, 3 minus 10 is going to be a negative 7/15. And again, also remember with fractions, that's a negative 7/15. You could also write that as a negative 7/15 or a 7/15, right? It doesn't matter if the negative's in the numerator, denominator, or in front. Just don't put it in both. Now, this idea of identifying the common denominator is very important, because students have trouble once we introduce variables, and they kind of forget, like, what do we do then if it's x, x plus 5 and x plus 3? Rather than 5 and 3. Well, this idea of multiplying the two denominators really comes in handy in a problem like this, because identifying what does x plus 5 and x plus 3 both divide into is a little bit more abstract, and it's a little more confusing for students to think about. Now, obviously, once we get into polynomial division, we can make a little bit more sense of it, but if we're just going to kind of focus on identifying a easy, quick LCD, we know that the product of those two denominators will produce a common denominator. So therefore, in this case, I will just multiply by x plus 3 on the top here and an x plus 5 on the top over here. Okay, now by doing that, I'm going to have x times x plus 3 all over x plus 3, and then minus a 2x times x plus 5 all over a, oops, I'm sorry, I forgot to multiply the x plus 3 times x plus 5. Now you could save some time by not rewriting, by understanding, and actually let's save us some time here. Rather than rewriting the denominator twice, because you can see it's a lot, right? We just know that the common denominator is going to be exactly the same. So let's go ahead and just rewrite it as one common denominator. Okay, now we just simply need to apply the, simplify the numerator here, so we can apply some distributive property and then kind of simplify, see what can happen up top. So therefore we get an x squared plus 3x minus a 2x squared, let's see, minus 10x. And that's going to be over. Again, you can multiply these out, but a lot of times when we're dealing with rational expressions, leaving them in the factored form is going to be preferred. And then here on this right hand side, you can see that we can combine this x squared minus 2x. Those are like terms, right? And these are like terms. So x squared minus 2x is going to be negative x squared, and 3x minus 10x is a negative 7x. And then you could factor out a negative x if you wanted to. But again, it really just kind of comes into now we're just, determining what is the best way we want to represent it. I'm not saying one way is going to be better than the other. You just need to kind of be understanding that you could factor out an x, you could factor out a negative. There's a lot of different ways we could represent this rational expression, but there's nothing else that we can do to further simplify it. Which is important to think about here when we want to, obviously always look to simplify your fractions as well as simplifying rational expressions. All right, for the next one, we have 5 divided by 1/3. Now, this one's really important to understand the division, that dividing by something is the same thing as multiplying by its reciprocal. So every single time that we have fraction operations with an integer, you can always think about this as putting it over 1. So we have 5 divided by 1, 5 over 1, right, or divided by 1, divided by 1/3. And again, it's important a lot of times when we are doing our operations to rewrite subtraction as addition, right? Or also writing division as multiplication. So I would just rewrite this as 5 over 1 times, actually let's write it like this, 5 over 1 times 3 over 1. Now some people say, well, how do you know that? Like, how can you do that? And let's go ahead and think about it this way. If I did 5 over 1 divided by 1/3, right? So basically I have a number or a fraction divided by another fraction. Well, there's too many fractions here, fraction here, fraction here, fraction there. So if I want to get rid of a fraction, I'm going to multiply by the reciprocal. And again, to keep a fraction the same, you have to multiply by the reciprocal, or you have to multiply in the numerator and the denominator. Well, 1/3 times 3 over 1 is 1. And then over here, you can see we're just going to have 15 over 1. So 15 over 1 divided by 1 is just going to be 15. And again, look at what our case is here. That's just equal to 15. So a lot of times it's just easier to think about, instead of dividing, is multiplying by the reciprocal. So that's exactly what I'm going to do here. I'm just going to rewrite this 5x times x minus 3 over x. Now in this case, I recognize that I have a variable in the denominator and numerator that is, since it's separated by multiplication, I can actually simplify this out. So therefore this can simplify to 5 times x minus 3. So the x's actually are going to divide out, and then I can just apply a nice little distributive property here to give me a 5x minus 15. All right, let's get into factoring, because last training I kind of just breezed through the factoring process, and we're going to be covering a lot of different factoring. So I wanted to separate the factoring, at least for this second training, just to spend one full slide on understanding this idea of factoring. And again, factoring is rewriting an expression as a product. So if I can take these four expressions and rewrite them as a multiplication problem. That's basically as a product. And hopefully you remember from last training or just from your previous understanding that trinomials can be separated into a product of two binomials. Now, there's a lot of different ways to understand this and work through it. But again, when I talk about the speed for this lesson or for this goal, I want to say, like, what can we do in our head? So if this is going to be a product of two binomials, right? So if all these trinomials, if they're factorable, that means they can be factored into a product of two binomials. So let's go and think about these two binomials. All right, well, if we're going to do FOIL, right? If you just kind of remember FOIL. So first, right, outer, and then you have the inner and the last. So this is basically what you multiply to get your trinomial, okay? So you have the first term, and then you have the outer terms. That's not the outer terms. Yeah. No, first, outer. I wrote that all wrong. That was horrible training. Sorry about that. Let's fix this. Let's just kind of do, here, let's do this. A plus B times C plus D. Okay, so these are the first, the outer, the inner, and the last. There we go. Good old FOIL. It's been a while since I taught FOIL, I guess. So anyways, the first two terms are going to multiply to give us our first term in our trinomial. So what two numbers or what two variables obviously are going to give us x squared? Well, that's going to be an x times an x. The last two terms, these outer or the last two terms, those are going to multiply to give us 4. So what two numbers could we do there? Well, we could obviously do 4 and 1, or we could do 2 and 2. The important thing we need to understand, though, when we're doing factoring is those middle terms, that inner and the outer, those add up to give us this 5x. So 2 plus 2, obviously, if we did 2 times 2 is 4, right? But they have to add to give us 5. Well, 2 times 2 gives us 4, but 2 plus 2 does not give us 5, right? But if we did 4 times 1 equals 4, and then 4 plus 1 is equal to 5. Now, again, it could also be -4 and -1, but -4 plus -1 does not give you 5. That's why I know the product here is there. And again, let's just kind of go through this so I'm not confusing anybody that was actually trying to learn that. So if you did first, right? So first, that's x times x, which is x squared. The outer, which is going to be x times 1, which is x. The inner, which is 4 times x, which is 4x. And the last, this is going way back, I haven't done this in a while, which is 4 times 1, which is 4. So then you just combine your like terms and you get x squared plus 5x plus 4. And you can see how that works when you're multiplying using the FOIL technique. Preferably, just like to use distributive property, but either way. So the reason why I wanted to kind of go through that, though, is again, so you can visualize seeing what you're trying to do in your head. Because in here, you can say, all right, I have a 4. What two numbers multiply to give you 4? Thinking 2 and 2, 4 and 1. But now they need to add to give me a -5 instead of a +5. Well, this is important because I don't need to change the numbers. I just need to change the signs, right? And everything is done. The next thing, again, I have a -4. Okay, well, what two numbers multiply to give me a 4? Got it. But again, it's negative. That means one of my numbers has to be negative, right? Because you can't have two negative numbers give you a negative. And the difference between those two numbers is going to give me a +3. Well, it can't be -4 and +1 because that would give me a -3. So this one has to be x plus 4 times x minus 1. And this one is just going to be the exact same, but now you can see this is a -1. So x minus 4 times x plus 1. And some of you might say, well, what would happen then if it was, what would it look like if it was 2 and 2? Well, there's two problems. You could do x squared plus 4x plus 4. That would be a x plus 2 times x plus 2. You could do an x squared plus 4x minus 4, which would be an x minus 2 times x minus 2. And if you did have a negative, you'd have an x squared minus 4, which would be difference of two squares, x minus 2, x plus 2. So I didn't include those as the problems because I wanted students to kind of look at these 4 examples and just kind of see, once you know that one combination, You just alterate or change up the sign in your head to get the product that you need. All right, the next one is rational expressions and equations. So we got into fractions and it's like, yep, let's do more of this. And one of the things that we kind of, I talked about up here was this idea of getting rid of fractions in the denominator, okay? And we also talked about the LCD. So it's really important, this idea of the LCD and getting rid of fractions in the denominator. If I wanted to get rid of this fraction, I multiplied by 3. Right? Which was basically this LCD here in this case, or you could also think about it as the reciprocal. So in this case, you can see that we have a lot of fractions, even more than what I did before. I have 1, 2, 3, 4 fractions. Now you could say that the common denominator is going to be a product of this, this, and this, like pretty confusing stuff. But first thing we always want to do, always in math, is always look to simplify. So in this case, I'm going to simplify this x minus 3, x plus 2. And you can see that that is factorable, right? So cool, we got that factored. And now you can also see that x minus 3 and x plus 2 multiplied is right there, right? So it's the same LCD. So we're still going to list the LCD here, right? So LCD is equal to x minus 3 times x plus 2. Now, if you want to combine these fractions in the numerator to one whole fraction, that's fine. And then you'd have a fraction in the numerator, fraction in the denominator, and you can apply the exact same technique that I did in the previous lesson or in the previous, in the fraction operations slide. However, I like to kind of move past this a little bit quicker and say, all right, if I have more than one fractions, I want to just find this LCD and multiply everything by the LCD to get rid of all of my fractions. So watch what happens. There's nothing wrong with combining your numerators to get one single fraction and then doing a fraction divided by a fraction. But in my opinion, it just kind of takes a little bit more work, because if I recognize this is the common denominator, that means x minus 3 divides into that, x plus 2 divides into that, and of course, x minus 3 times x plus 2 divides into itself, right? So how many times does x minus 3 divide into this? Well, the x minus 3's would divide out, leaving me just with an x plus 2. Therefore, I'd have a 4 times x plus 2. So what you're basically doing is you're multiplying this times every single expression. When I have this times 5 over x plus 2, the x plus 2's will divide out, leaving me just with a 5 times x minus 3. And then when I multiply this expression times the denominator, obviously this and the denominator are going to divide out, just leaving me with x. So now you can see I have simplified these four fractions into just one single fraction. And now all I simply need to do is just go ahead and simplify and we're good to go. So I'll have a 4x plus 8 plus a 5x minus 15, right? Just applying some good old distributive property. And then that's going to give us now a 9x minus 7 over x. And you could distribute the x if you wanted to, or preferably just kind of leave that just right there. And there you go. Now, it is also important to understand, though, that we cannot divide by 0, right? So a lot of times when we're doing these, we just want to make sure that we apply the restrictions. So in the original problem, we know x cannot equal 3. In the original problem, we know x cannot equal -2. And then once we get into this simplified version, we also recognize that x cannot equal 0, right? And again, this just kind of goes back to our idea of not dividing by 0, which obviously we get in much more in depth in the course. But it's very important to remember that we cannot divide by 0. So those values cannot be a part of that expression. And that also becomes very, very important in this equation. So previously, up to this point, you guys dealt with equations that we could just solve, and it was fairly simple. Well, in this one, we have a lot of these rational expressions, and they don't look like that much fun at all. So, but this idea of multiplying everything by the LCD is very important, because when we multiplied this, what we call a complex fraction, by the LCD, what happened is we got rid of all of these extra fractions, 1, 2, 3, right? We got rid of them all because the denominator divided into the LCD. So if I want to solve an equation without fractions, I can also do the same thing. I can multiply by the LCD. Now, obviously, I tried to keep things streamlined a little bit for this lesson, so I kept the LCD exactly the same. You can see x squared minus x and times x squared minus x, same thing. So what I'm going to do here is I'm going to do exactly like I did in the last example. I'm going to multiply this everything by x minus 3 times x plus 2. So again, when we multiply this, the x minus 3's divide out. We're going to be left with 4 times x plus 2. The x plus 2's divide out. I'm going to be left with a 5 times x minus 3. And then obviously that's going to equal us with an x. Now again, we're going to need to do our distributive property. And we have a 5x minus 15 equals x. Now we have an equation where our variable is on both sides. So now we need to get the variables to the same side and get everything else to the other side. So let's just go and add a 4x plus 5x is going to be a 9x minus 7 equals x. And then we'll just subtract the x on both sides and add the 7 on both sides. So therefore I have an 8x equals a positive 7 divided by 8 and x equals 7/8. Now again, this is a solution to this equation, but just like we understood that when we have fractions, we understand that there are numbers that cannot be, right, included as a solution. If they are, they're what we call extraneous. So thankfully, if you look at this, our excluded values here are going to be 3 and negative 2. Like those are the values that make our denominator equal to 0, not 0 in this case. And 7/8, obviously, if you were to plug it in for x, would not make any of our denominators equal to 0. So this solution is verified from there, as long as I did all of my math right. All right, on to the next one is for trigonometry. So for trigonometry, we kind of just want to kind of go back and review some of our trigonometric functions, especially like the Pythagorean theorem and our sine, cosine, and tangent. So really what I'd like to remind you for the Pythagorean theorem is our Pythagorean triples. I think those are extremely important for you guys to increase the speed at which you are doing our trig problems. So hopefully if you recognize, sorry, and these are all right triangles, obviously. Well, not obviously, but obviously if we're doing trigonometry and Pythagorean theorem, they need to be right triangles. But anyways, the nice thing about this, if you recognize a Pythagorean triple, then you know what the hypotenuse is. Done. All right, so obviously there are a lot of Pythagorean triples. The ones that we're going to focus on, or you're going to come into contact most often in precalculus, I would say is the 3, 4, 5 triangle, the 5, 12, 13 triangle, and the 7, 24, 25 triangle. Now, the nice thing about these is you can also double each one of these. So for instance, you can see that if I double this like 3, 4, 8, that would be the 6, 8, 10 triangle, which again, you can see here is right over there. So each one of these, you can just keep on doubling them to get more Pythagorean triples. Obviously, to keep numbers rather simple, you're going to see these Pythagorean triples a lot. So I would recommend knowing these or remembering them. But again, let's say you forgot. So a squared plus b squared, let's just kind of go through this. So remember the Pythagorean theorem here is a, b, and c. So a squared plus b squared equals c squared. Or another way to think about that is that leg squared plus leg squared equals the hypotenuse squared. So let's just verify that this is correct. So if I did 3 squared plus 4 squared, that should equal my c squared. So 3 squared is 9, plus 4 squared is 16. And therefore that would be 5 equals c squared. Take the square root of both sides. You could say c is equal to 5. Now it's actually really important here to recognize that because, what about when you have radicals? Usually students are like, I got the Pythagorean theorem, but then we throw in radicals and they're like, I don't know the Pythagorean theorem. So let's just call this x, right? You could call it b, you could call it c, a, elemental p, doesn't really matter. But we recognize that's why I said leg squared plus leg squared equals the hypotenuse squared. So 4 squared plus x squared equals 3 square root of 2 squared. And again, without a calculator, we should be able to compute this. So 4 squared is 16 plus x squared. Now 3 squared of 2. Again, 3 squared of 2 squared is, you got to remember, that's 3 squared of 2 times 3 squared of 2. So what we talked about last class period, multiplying radicals, 3 times 3 is 9. Square root of 2 times square root of 2 is 2. So that's going to equal an 18. Now we can just subtract here and we get x squared is equal to 2. So therefore, x equals the square root of 2. Now again, you could think about that as the plus or minus, but we don't have any direction here in this triangle. So therefore, we will just say that is going to be a positive square root of 2. All right. Now let's go and talk a little bit more about the, let's call this the hypotenuse. Let's talk about our trigonometric functions. So our trigonometric functions is just a comparison. That's all they are. How big is one side of a triangle compared to another triangle based on the angle? And that's the thing where I think a lot of students get mixed up on is when we're dealing with, and again, I'm just going to focus with the sine, cosine, tangent. When I say the sine of theta, that means I am comparing the opposite side to the hypotenuse based on my angle theta. So the nice thing about knowing the Pythagorean theorem is we know that the hypotenuse is always directly across from my 90-degree angle, right? So let's just kind of say, here's my right triangle. So therefore, this is my hypotenuse. Okay, now the side of the triangle that is directly across from the angle is what we call our opposite side. And the side that is directly between my angle and my 90-degree angle is what we call our adjacent side. Okay, so the sine of an angle is simply the opposite over the hypotenuse. Okay, now if I was going to do theta, you can say that hypotenuse is 10, right? But the opposite side is going to be 8. So it'd be 8 over 10. Now I'm not going to simplify them just for, actually whatever, I can simplify it. So that's going to be 8 over 10, which you can reduce to 4/5. All right, and let's just maybe move this over a little bit just so I have enough room. Okay. And then we can get into the cosine of theta, which is going to be the adjacent over the hypotenuse. And the adjacent over the hypotenuse is 6 over 10. 6 over 10, which again, you could divide the top and bottom by 2, so that's 3/5. And then last but not least is we have the tangent of theta. So the tangent of theta is opposite over adjacent. And again, when I'm saying opposite over adjacent, I'm really saying how big is the opposite side compared to the adjacent side, right? How big is the opposite side compared to the hypotenuse? So you can see that relationship of comparing. So opposite over adjacent. And that's going to be 8 over 6, which is 4/3. Okay? Now again, this is all based on this angle theta. So here is my hypotenuse. Here was the opposite side, and here was the adjacent side. What's important about this is all of this changes if I start to call my angle theta or alpha up here, because the hypotenuse doesn't change because that's always the largest side, right, of a right triangle. However, now this is my opposite side and this is my adjacent side. So you got to see that the relationship of those angles matters based on the angle that we are referring to. So now when I say what is the sine of alpha, it's not going to be the same as the sine of theta. The sine of alpha is now going to be 6 over 10, which is 3/5. The cosine of alpha is now going to be 8 over 10, which can be simplified to 4/5. And then the tangent of alpha is going to be 6 over 8, which is the same thing as 3/4. So it's just very, very important for you to see how the relationship of the angles matters. And all right, and then last for this one is just going to be simplifying some radicals. So obviously, taking the square root of a number is simplifying a radical, and that is fairly basic. Square root of 4 is 2, because reason why that works is what we're asking for the square root of 4, we're really asking for what number multiplied what other number is going to equal 4, right? That's what we're looking for. What number multiplied by self is equal to 4? And I'm not sure if that equals each other, so let's not do that. But that is going to be 2 times 2, which equals 2. All right, so just understand that is what we're looking for when we're dealing with the square roots. Now, to simplify radicals, for instance, square root of 12. There is no number, integer, that multiplies by itself to give you 12. However, we can break that up into square root of 4 times 3. And the reason why I'm breaking this up is nice because we know what the square root of 4 is. The square root of 4 is 2. We don't know what the square root of 3 is, so we're just going to leave that on the outside. So that's 2 times the square root of 3. And now that is simplified. So whenever we have radicals in the numerator and denominator, it's always helpful and important to simplify them first and then simplify the fraction. So in this case, we could have 2 radical 3, right? We just figured that out, over 12. Now we can reduce the fraction. 12 over 2, you can multiply 2 on the top and the bottom to give you a square root of 3 over 6. All right. And then hopefully you recognize here, it's going to be the exact same thing. We're going to have 12 over 2 square root of 3. Now I have 2 over 12, right? But instead of, you could divide the top and bottom by 2, or you could just say that 2 divides into 12 6 times. All right. And then a lot of times what we're going to be doing in this class is rationalizing the denominator, which is basically just a way for us to get rid of the radical in the denominator. So to do that, I'm just going to multiply by the radical on the top and the bottom. And what that's going to do is that's going to produce 6 square root of 3. And remember, square root of 3 times square root of 3 is going to be the square root of 9, which is 3. Okay, so what that does is that produces now a fraction where there's no more radical in the denominator. And now I can just simplify that one more time to give us 2 square root of 3. And there you go, ladies and gentlemen, for the math portion of it. Just a quick little review. What we covered is we covered fraction operations, more factoring, rational expressions and equations, triangles and trigonometry, as well as simplifying radicals. Now, a common question that I get from my students is, I appreciate all the work that we're doing here, but can't I just rely on my calculator for fractions, factoring? Isn't it just going to be faster? And the question to that is absolutely not. Yes, you can use your calculator, and when you have a test or when you have have access to a calculator, then yes, all the merry. Like, I think we need to be using actually more technology. The problem, though, that also comes into the mathematics is students, their reliance on technology for non-technological processes. And for instance, when we are having students, going into calculus and going into more mathematical processes, we need them to be able to do basic functions without the reliance on a calculator. Obviously, there is a lot more applications we can use with a technology that I think is going to be more important for us to be able to apply. But when I'm teaching precalculus, there's only 2 chapters that I allow my students to use the calculator. Everything else, it is slower for us to take out our calculator and to actually go ahead and try to type in the computation rather than using our brain and being able to compute everything. So that is why we are covering these foundational skills so that you guys know what you are doing and you're not going to be relying on a calculator. Even if you have a calculator, it is going to be faster for the types of problems that we are covering to be able to do them without a calculator than with.